In this video, we are going to talk about exponents. So there are a lot of rules for handling exponents. And this is going to take a while to go through them, but I'm going to try and organize them in a way that hopefully makes them easier to remember. And of course, we're going to work through a lot of different examples. But these rules are super important to get down for a number of reasons. One main reason is because when we deal with polynomials later, and polynomials is a big topic that you cover in beginning and intermediate algebra, you're going to have to use the rules for exponents when you're multiplying polynomials together, when you're raising them to a power, when you're doing different sorts of operations with them, factoring. So that's important that you understand exponents there. But exponents are just important in general. They're used a lot in math and algebra, and they really form the basis for exponential and logarithmic functions, which is very important classes of functions that you would study really starting in intermediate algebra. We're not going to do those kind of functions in this class, but in intermediate algebra, you would look at exponential and log functions. So this is really important stuff. And it's also important for radical expressions. So again, intermediate algebra, you study radical expressions. So that means square roots, cube roots, other types of roots, higher roots. And manipulating those, it's very helpful to know exponent rules. So there's a lot to go through here. And I'm not going to say that it's going to be easy all the way, but we're going to go through them step by step. And for each of them, I'll give several examples, and if you need to watch this video more than once, that's fine. But it's really important that you get this as we go forward in what's coming up in the future. So there are 9 exponent rules we're going to go over, but I'm not going to do them all at once. So what we're going to do is take usually a couple at a time. They come in kind of pairs. There's one that's a little bit, different from the others, but basically we're going to do them in pairs. And after every pair of rules, we'll do some examples. So we'll go over some rules, then some examples, rules, examples. Okay, so the first two we're going to look at have to do with what happens if you're multiplying two exponential expressions. So exponent means you're raising to a power. What do we do with this if we have the same base? So there are two main rules here. If you multiply two of these together with the same base, we actually add the exponents. If we divide with the same base, then we're going to subtract the exponents. So these are called the product rule and quotient rule. You want to kind of visualize what's going on here. So let's say you had 7 raised to the 13th power times 7 raised to the 5th power. Now, I made those numbers big enough so that you're not going to actually think about what the number 7 to the 13th power is actually written out. That doesn't matter. What you want to do is think about this as 7 to the 13th. Since exponents are repeated multiplication, this is really 7 times 7 times 7, ... And this is going to be with 13 factors. So you actually imagine all those 13 factors being written out. And then we're going to multiply that by some more factors of 7 where there's 5 written out. Well, what happens if you have a bunch of factors that you're multiplying together? You have this many factors over there and this many factors over here. When you multiply them all together, they just all come together. And so the total number of factors is the sum of the number of factors of each. So the power is telling you how many factors. So I have 13 factors here and 5 factors here. Together, those make 18 factors altogether. 13 plus 5. And that is really why. That's how you should understand the product rule. Again, all of these rules that we're doing, and this applies for almost anything you learn in math, you can memorize the rules, and you should memorize the rules. You should strive to be able to write down the rules whenever you're asked them. But if you really want these things to stick, and you really want to use them in a way that's intuitive and that comes to be second nature, you really want to have a mental picture of what's going on that gives you an understanding. So instead of just memorizing, okay, if the same base, I add the exponents. That could leave you next semester or a year later, you might forget that. But if you understand it, this mental picture of there's factors over here and there's factors over here, and I'm putting them together, and that's why I add, that's going to stay with you the rest of the time that you do algebra and math. So that's why we get 7 to the 18th here. Now, I should say that for all these rules we're doing so far, we're only assuming whole number exponents. So positive integer, 1, 2, 3, 4, 5. However, everything we're doing later can be extended to any real number exponents. We're not going to do it in this class all the way. We will do 0 exponent. We will do negative exponents. But we're not going to do fractional exponents. We're not going to do general real exponents, so like irrational exponents. That would be for an intermediate algebra class. Or if you're taking, I guess since we're not going to have intermediate algebra in the future, it would be like a co-requisite class that you're taking with another class. But all of these rules will work for any exponent. And so that's the reason that these are such powerful rules, is you can make intuitive sense of them with whole number exponents. You can have a mental picture of what's going on, why they're true, but they work even if those exponents are not whole numbers, even if they're 0 or negative or fractions or irrationals. Now let's look at the second rule. So this was an example number 1. Why is the number 2 true? Well, very much the same reason. Let's say we take, 6 raised to the 32nd power divided by 6 raised to the 5th power. Again, you could think there's 6 times 6 times 6. And notice here, I'm deliberately taking a power that's bigger on top. Now, if the power on the bottom was bigger, we'll get to that later. But for now, I'm just taking a bigger power on top. Notice there's 32 factors here, divided by 5 factors on the bottom. In fact, let me add a few more factors here, just a second. Now, if you have more factors on top, you get 32 on top, 5 on the bottom. That means you can cancel. Remember, you can cancel factors. This is just like with fractions. If you have a factor of 3 on top and 3 on the bottom, you could cancel those. So you have a factor of 6 on top, 6 on the bottom. So all those 5 are going to cancel here. Cancel, 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 cancel. Till eventually all the ones on the bottom cancel, leaving 1 on the bottom. And then we have what's left over. Well, if you have 32 factors on top and you get rid of 5 of them, that's subtraction. That's what subtraction means for whole numbers. Take away. So this is going to be 6 raised to the 32 subtract 5. So 6 to the 27th. Again, these are 27 left over. Now, the same thing is going to be true with variables for the base and variables for the power. So I just specifically used whole number, base, and exponent here. But the same holds true for, so a to the m times a to the m. You add the exponents, m plus n, a to the m, a to the n, over a to the n, a to the m minus n. Here, so in all of these rules, the base a is not going to be 0. So we don't want a base of 0, which for pretty clear reasons, because 0 to any power is 0. So that's just not something interesting, and so we can't divide by 0 anyway. So let's look at a few examples in the homework of these two rules. Okay, so first problem here. X to the 16th times x to the 4th. This is a direct application of that product rule. We add the exponents, x to the 20th. Remember, to do exponents, you can always hit Shift 6. That's the caret symbol, and that will get you into the exponent. Shift 6. And then add 20. So x to the 20th. Now, for this one, you have to remember that if there's no exponent there, that's really to the first power. So any number to the first power is just itself. So y times y to the 10th is really y to the first times y to the 10th. And now if you remember that's an exponent of 1, now you can add them. It's 1 plus 10 makes 11. So this is all going to be y to the 11th. You can have multiples. So in the examples I did, there was just 2 multiplied together, but this applies to any getting multiplied together. In fact, you could even have ones that are on top of a fraction, on the bottom of a fraction, and what you're going to do is add all the ones on top and then subtract off all the ones on the bottom. But we'll get to something that a little later. Okay, this is the next. Coming back to this one. Okay, so 5 plus 2 plus 3, so that's x to the 10th, because you add them all together. Okay, so this is the quotient rule. We've got a bigger power on top, y to the 8th, over y to the 4th, you subtract 8 over 4. A real common mistake here is to divide. So to say 4 goes into 8 twice and say that this is y squared. It's not divide. You don't divide the exponents. You subtract the exponents. Okay, so similar thing here. You could have, as long as it's the same base. So you work with the x's, subtract the exponent on the x's, and then subtract the exponents from the y's. Okay, and now we're getting to some other stuff. So now we're going to go back to talking about rules. Now there's a very special rule. This one is just an isolated rule, and we'll go over some examples. Okay, number 3. Number 3 is a rule that it has you have an exponent, an exponential expression that's raised to a power. So this is often called the power to a power rule, or at least that's what I call it. So it says, what if I take a power like this, and I decide to raise it to a power? So if you're not familiar with this, maybe let's think through what this should be. Let's work through an example. Again, I'm used like specific numbers. Let's say we had something like, I don't know, 13 raised to the 4th power, and all of this is going to be raised to the 3rd power. Okay, what's this going to be? Well, when you raise to the 3rd power, this means it's the base with 3 factors, but the base itself is 13 to the 4th. So it's 13 to the 4th times 13 to the 4th times 13 to the 4th. And now what you need to realize is this is the product rule. So it's 13 raised to the 4 plus 4 plus 4, where there's 3 terms. Well, what happens when you repeatedly add integers together? That's multiplication. You can even visualize this a little more by, you could even think of it as 13 times 13 times 13 times 13 times. So actually think, if you want to think all the factors of 13, you can visualize those 13 to the 4th. Oh, there's 4 13s there. There's another 4 factors of 13 here, and there's another 4. So it's really saying there's 3 groups. There's 3 groups with 4 factors each. So this is like saying I have some sports teams, there's 3 sports teams, and every sports team has 4 players. If you have 4 players on a team, and each team has you have 4 players on a team, and there's 3 teams. How many players you have? That's multiplication. That's one way you should think about multiplication. So this is another way you can think. There's 12 total. 12 factors total. So what we end up doing when we raise a power to a power is we multiply the exponents. So this would be 13 to the 4 times 3, just 13 to the 12th. So a to the m, all raised to the n, is going to be a to the mn. And this, again, this is what I call the power to a power rule. Again, let's go to the homework and look at a couple examples. So x to the 10th, all raised to the 5th power, we multiply those exponents. X to the 50th. Now, you have to be very careful with negative numbers. So the thing that you want to keep in mind with negative numbers is if you raise negative number, or if you raise a negative 1, if you raise it to an even power, it's going to be positive. Think of all the negative numbers. If you're raising to a power, it's repeated multiplication. Since a negative times a negative is positive, if you're raising it to an even power, they're going to pair up, right? So if you raise it to the 10th power, there'd be 5 pairs. You get minus, 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 minus. Each of those pairs is positive, so at the end, they all multiply to positive. But if you raise a negative number to an odd power, then there's going to be 1 left over. So they're all going to pair up to make positive, but there's 1 left over. So you see that when you raise a negative number to a power, it depends whether the power is even or odd, whether it's negative or not. Now, this one, we could do what's inside here and say, well, what's inside here is minus 15 cubed. Or we could just say, well, let's look at negative 15 as the base and just say it's negative 15 all raised to the 12th. So that's just using the power to a power rule. And now we're going to take care of the minus. We don't want to leave the minus inside the base. So now we're going to take care of the minus. And since now 12 is an even power, we can take away the minus. So negative 15 all to the 12th is 15 to the 12th. It's positive 15 to the 12th. Okay, so that's a really important thing to remember about negative numbers. Depends whether you're raising to an even or an odd power. Yeah, so I think this is all we're going to do for this right now. We need a couple more rules. You need to know, like, at least like 4, 5, 6 rules before you're really able to do some interesting expressions, because what you're going to be doing is using a lot of these rules in combination with each other. You hardly ever use just one rule in isolation. You're using 2 or 3 or sometimes 4 rules at once. And that's why they need to be second nature, because if you're having to consciously think about each of them individually, it's going to be very hard to put them together in a single problem. Whereas if you have a more intuitive understanding, then you can kind of combine them more easily in your mind. So let's go to the next pair. These are also called a product and quotient rule, but they're slightly different product and quotient rules than the first 2. All right, so number 4. This is a product rule, but instead of multiplying 2 expressions together, the base is a product. In other words, we have AB, A times B, and we're raising it to a power. And what this rule says essentially is that you can distribute exponents across multiplication. Now, if you remember, we cannot distribute exponents across addition. That's something we're going to learn with polynomials later. A really common mistake is to try and say that, for instance, a plus b all squared in parentheses is a squared plus b squared. That is not the case. We cannot distribute exponents across addition the same way we distribute multiplication across. But we can distribute exponents across multiplication. That we can do like this. So this is in fact going to be a to the n times b to the n. Again, why? So here's a reason. Let's say that we had 3 times 17, all raised to the, let's say, 5th power again. Okay, now this means I'm going to write out 3 times 17, 3 times 17 times 3 times 17. So what I've got is 5 factors, and each of them has a factor of 3 and a factor of 17. Well, multiplication is commutative. When I'm multiplying a bunch of numbers together, it doesn't matter what order I do it in. So I can regroup. It's really you're changing the order and you're dealing with parentheses and all that stuff. But at the end of the day, you can put all the factors of 3 together and you can put all the factors of 17 together. So I can regroup this to collect all the 3's in one product and all the 17's in one product. And of course, then that's 3 to the 5th times 17 to the 5th. So this is how you should remember it. Why does it work? Because if I were to imagine that whole product, AB, 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 then when I write all of those factors of A and B out, I could collect all the A's together, and that would make one product, all the B's together. And so now I have my A to the power and B to the power. Again, the intuition works for whole number exponents, but it turns out to be true for any exponent later. So this is called a product rule. There's another one that's very similar to this, A over B to the n. And what this says is that you can distribute exponents across division. And this one is even a little bit simpler to see because, let's say we take 23 over 11 all raised to the 4th. Okay, so what is this? Remember, this is now 23 over 11, 23 over 11. So in this case, this just follows from how we multiply fractions, how fraction multiplication is defined. When you're multiplying fractions, you multiply all the numerators together, you multiply all the denominators together. So if I have the fraction a certain number of times, I'm multiplying those numerators together that many times. So I got 23 to the 4th. 23 times 23 times 23 times 23. And I got 11 to the 4th. 11 times 11 times 11 times 11. And that's really what's going on here. So this shows that you can distribute exponents across division. It's really easy to get these mixed up with the first two. They both deal with the interaction between multiplication and division and exponents. The difference is, in one of them, you're multiplying or dividing the exponential expressions together. In this case, you have a product or a fraction inside the base. That's the difference. And there's really only one power. So they're very similar, but they are different. So I guess I'll call these product rule number 2, quotient rule number 2. Let's look at some examples. Okay, here's a typical example. Now, in this case, it's not two variables multiplied together. It's a coefficient times a variable. Same idea applies. Distribute the 3rd power across. So 6y all raised to the 3rd power is 6 to the 3rd power times y to the 3rd power. Now, for powers that are less than 1,000, you really should have the powers that evaluate up to 1,000, 10 cubed, memorized. So you should have 6 cubed, 7 cubed, 8 cubed, 9 cubed, 10 cubed. And then as you get to like the 4th and 5th powers, it doesn't take very long to get bigger than 1,000. But that's generally my rule of thumb. If I'm doing a paper and pencil test for a class, my rule is you need to know, if they don't have calculators, you need to know and evaluate all whole number powers to a whole power up to and including 1,000. So this is one of those. This is 6 cubed. So I didn't need to work this out, or if I remember it, and it's 216. So this is 216y cubed. If it's a power that is bigger than 1,000, then you can just leave it. So if it's like, 13 to the fourth, and you're not using a calculator on the exam, I would let people just write 13 to the fourth. I mean, we did this before in the examples. But 216 is small enough that we're going to write that down. Okay, now, this is negative 11x all squared. So first thing to realize is we're distributing the exponent, but also there's a negative. So you have to remember what we talked about with negatives raised to a power. A negative number raised to an even power is positive. So I'm not going to have a negative sign here. 11 squared is 121. And then I distribute the 2 across x and get 121x squared. Okay, let's look at this last one. Again, we're distributing the exponent and then going power to a power. Now, this one, so we're already combining a couple of rules here. So we're combining distributing the exponent and we're combining power to a power. So we're using, I guess, numbers number 4 and number 3. Now, you don't have to think about the numbers like, oh, this is rule number 3 or rule number 2. Again, if you use these enough, they're just second nature, and you don't, like when I was preparing this video, I had to actually stop and write them down because I was afraid I was going to miss one. I was going to forget about it because if you use these all the time, you don't consciously think about them. So I had to consciously think about which ones I had to go over. But here, we're using the 2 in combination, so we distribute across, so 3 squared. X squared squared, power to a power, we multiply 2 times 2, x to the 4th. So if it was 3x to the 5th, all squared, it would be x to the 10th. So it's 2 times 2, not 2 plus 2. Let's see. I think we're ready for the next, we're ready for the next rule. So let's go back. And now what we're going to tackle is, what does it mean to raise to the 0 power or to a negative integer power? How can we possibly make sense of that? Okay, so this is going to be rule number 6 and 7. Again, remember the base is not 0. So 0 to the 0 is undefined. But any other number, any non-zero number raised to the 0 power is defined to be 1. Now, why is it 1? So again, you could just say, because I said so. And this is probably what a lot of teachers say. If somebody asks, why is raising to the 0 power equal to 1? And the teacher says, because I said so, because that's the rule, just memorize it. But let's see if we could try and convince ourselves. If you didn't believe this, or say you're on, you're at lunch with somebody and they say, hey, what's something to the 0 power? And say, what's 1? And they say, well, why is that? I don't believe that. Could you try and convince them? So here's one way you can think about this. One way to think about it is just kind of manipulate the rules that we have earlier. That's kind of a formal way of doing it, but that's kind of less convincing. So for instance, I could say, well, what's 5 to the 0? And I could say, well, that's 5 to the 7 minus 7. Oh, you could say, well, wait, 7 minus 7, where'd that come from? Well, okay, it's true. 7 subtract 7 is 0. By that quotient rule, this is 5 to the 7th divided by 5 to the 7th, right? It's going the other direction. But we know that this is equal to 1. This feels like it's a little bit like cheating, maybe. Let's see if there's a better way. Let's look at powers of 5 on the side here. We got 5 to the 4th, 5 cubed, 5 squared, 5 to the 1st. Okay, and now we want to keep going with this table and get 5 to the 0. Well, 5 to the 1st, we know is 5. Of course, 5 squared is 25. times another 5 is 125, and finally 625. So that's the biggest power. The biggest power of 5 that you should know is 5 to the 4th. That's also the biggest fourth power. So 625, 125, 25, 5. Now, what is the pattern as I'm going down this list? In other words, to get from 625 to 125, from 125 to 25, from 25 to 5, what operation am I doing each time? Just take a second to think about that. So hopefully what you should be recognizing is that to get from one of these numbers to the next one, and so you can see this most easily from 25 to 5, 125 to 25, but also 625 to 125. I'm dividing by 5 each time. That is the pattern. Math is all about finding patterns and exploiting patterns. So I see a pattern here. I'm always dividing by 5. So what do I get if I keep continuing the pattern? We want to continue the pattern, right? The exponents are decreasing by 1, 4, 3, 2, 1, 0. So the exponents are decreasing by 1, and the numbers I'm getting by dividing by 5. So I divide by 5 again. What's 5 over 5? 1. 5 divided by 5 is 1, not 0. So this is very important to remember. Raising to the 0 power is not equal to 0. Okay. Now, what we're going to do is I'm going to go over some example. We're going to go over a number of different expressions here. And it's one thing just to know, oh, okay, to the 0 power is 1. I understand that. But where people really make mistakes is how this interacts with the order of operations. So I'm going to do a number of expressions here. I'm going to put them up here. And then I want you to pause the video and take a few minutes to work through them. There'll be, I think there's like 10 of them. And just fill them in. And then when you're done, unpause the video, watch, and then go through and see as we go through. And most people will miss at least a couple. And so that's going to show you that you need some you have to think again about the order of operations here. So let me pause the video and put up these problems, and then you can go ahead and pause the video and work through them. Okay, so here are the problems. There are, I guess there's 16 of them. Huh, it's a little more than I said. So some of you notice these are very similar expressions, but the one thing they have in common is they all involve exponents, even or small, even or odd, like exponent 2 or 3, and exponent 0, minus signs, and parentheses or multiple, like parentheses and brackets, all grouped in various ways. So go through these 16, pause the video, write all these out. Now, all you need to know for computation is that 5 to the 0 is 1, 5 to the second, 5 squared is 25, 5 cubed is 125. So that's not the issue. The issue is, are they positive or negative? How do they, for the last 4, how do they combine? So go ahead, pause the video, take as much time as you need, and come back and we'll go over these. Okay. Okay. So I'm going to assume that you have worked through these on your own, done them the best you can. Let's see how you did. Now, if you missed some of these, don't feel bad about it. I've done this with dozens of classes over the years, and there's always confusion on these things. People always are getting mixed up on how the order of operations interacts here. So let's start with this first one up in the upper left corner, minus 5 to the 0. And in fact, let's do all 3 of these. Very common for people to just immediately get these wrong. So is the first one, is it 1 or negative 1? It's actually negative 1. The second one here, minus 5 squared, is minus 25. And this is minus 125. Now, A lot of people say all these are positive. If you are doing that, what you're doing is you're confusing the order of operations between multiplication and exponents. For instance, minus 5 all squared. The base is not negative 5. The base is 5. What this is really saying is negative 1 times 5 squared. And because we do exponents first, you want to do this first to get 25 and then multiply by negative 1. So it's 5 squared is 25, and it's the opposite of 5 squared, negative 1 times 25. And that's the same for the other two. That's why all three of these are negative. Now, if you were thinking, oh, but the base is negative, it's negative 5, all raised to this power. You need the parentheses around the base. So that's the difference between those three and these three. In these three, the parentheses establish the negative 5 as the base. So now it's just the number negative 5 raised to the 0 power. Well, anything to the 0 power is 1. So we know that's positive 1. The number negative 5 squared, well, that's positive 25. Because negative 5 times negative 5 is positive 25, not negative. Now, the third one actually is different. This is why I put in an even and odd power. The third one is negative 125, but it's important you understand the reason. It's because it's a negative number raised to an odd power. So it's not just that the base was negative, because we saw with negative 5 all squared, we got positive 25, because 0 and 2 are even, so those are positive, but the negative 5 cubed is the same as without the parentheses because it's an odd power. What about the next three? So this one. Well, let's go through it. All of these actually are just the opposite of what's above. So for instance, this is saying take the opposite of negative 5 to the 0. Well, negative 5 to the 0, we just saw that that's equal to 1. That was above. So this is minus 1. What about this one? Again, negative 5 squared. Always do exponents first. Negative 5 squared. Negative 5, the number squared, is positive 25. So this is negative 25. And this one, because negative 5, the number negative 5 all cubed, is negative 125. This is saying what is the opposite of 125. So this one is actually positive 125. Okay, so notice this row, they're all exactly the opposite of the previous row. Let's take the last row. Now we've got brackets. And these brackets are very important because what these brackets are saying is everything inside the brackets here is the base. And then that's going to differ from the previous row. So this one is just saying, oh, just some number to the 0. Again, it doesn't matter what's inside there. Any number to the 0 is 1. So that's positive 1. But inside the brackets of these other two here, the minus is canceled. So this is just saying 5 squared. This is 25. This one is 5 cubed. It's 125. Because you can do everything inside the base first. Now we get to maybe some of the most confusing at the end because there's some terms. So it's a matter of identifying when something is a term versus a factor. So in 5 squared minus 5 to the 0, you have to identify that this is two terms that we're evaluating. There's 5 squared, which is 25, and then we're subtracting a second term, which is 5 to the 0, which is 1. So 5 squared subtract 5 to the 0 evaluates to 24. Now, the next one, what is different here? There's some parentheses. So I threw in some parentheses. The other three, I threw in parentheses, but I put them in different places. If I put the parentheses around the minus 5 to the 0, because there's no plus minus between the expressions, this is now all one term. And the secret operation here is multiplication. It's no longer addition or subtraction. So this is just saying 25 multiplied by minus 5 to the 0. Well, we already saw, we can go up here. That's that. We already saw that was negative 1. So this is 25 times a negative 1. So this is negative 25. Now, if I shift that parentheses from outside the 0 exponent to inside, this is going to change it again. It's still multiplication, but now it's 25 multiplied by negative 5 to the 0, which we saw was positive 1. So now it's 25 times a positive 1, positive 25. And the last one, I just put the parentheses all around a bunch of stuff here. And the important thing to recognize here is this is just something raised to the 0. So it doesn't matter what's inside here. It turns out it's 20, right? 25 minus 5. So this is actually 20 to the 0, but this is just 1. So we got 4 different numbers: 24, negative 25, positive 25, 1. You really need to look over all of these. If you need to go back, and if you miss some, go back and make sure you understand, before you go any further, make sure you understand which ones you got wrong, why you got them wrong, and what's the correct way to think about it. Because you have to, if you don't have this stuff down, the order of operations and exponents, you're going to keep making these mistakes over and over again. And it's going to be a real problem going forth in algebra for really a lot of the different things. Anytime you're learning stuff with polynomials or radical expressions or exponential log expressions, you're going to run into this kind of problem. So if you want to go ahead, pause the video, maybe look over this again or think about the ones you missed. And what I'm going to do now is go to some homework problems. Or actually, sorry, we have one more rule that goes with this. So this was raising to the 0. What about raising to a negative integer power? Let's go over that. So this should be rule number 7. 7. A raised to the minus n. Again, n is a whole number here. So this is going to be 1 over a to the n. Okay, now let's see why this is. Again, one way we could see this would be to say, well, let's say, what is 5 to the negative 2? 5 to the negative 2. Well, that's 5 raised to the 0 subtract 2. And then we could say, we want the same rules to hold. So we want these exponent rules to always be true. If the exponent rule is still going to be true, this is going to have to be 5 to the 0 divided by 5 squared. Now, we already just saw a second ago that 5 to the 0 is 1. So that means this is going to be 1 over 5 squared, which would be 1 over 25. But really just, 1 over 5 squared. In other words, a negative exponent means you divide by that corresponding positive power. But there's another way to see it. If you go up to this pattern up here that we use to discover the 0 power, excuse me just a second, okay. And let's put 5 to the negative 1, 5 to the negative 2. So just 2 more rows here. Let's continue our same pattern. Again, the powers are decreasing by 1, and on the numbers, the valuation of the powers, we're going to keep dividing by 5 over and over again. So the powers decrease. So I'm still going to divide by 5, divide by 5. So divide by 5. 1 divided by 5, that's the fraction 1/5. 1/5 divided by 5 is 1 over 5 squared, or 1 over 25. And what you can see here is that you're going to keep getting 1 over 5 to the negative 3. It's going to be 1 over 5 squared times 1/5, and so you get 1 over 5 cubed. So that's another way to kind of justify why we get this rule. Negative exponent means reciprocate, means divide by the corresponding positive exponent. Okay, so now let's go to the homework and look at some examples. Okay. 3 to the 0, 1. Okay. That's pretty straightforward. Again, be careful here. Where are the parentheses? The parentheses are the entire around the negative 2. So the base is the number negative 2. So this is 1. Without the parentheses, it would be negative 1. Okay, so without the parentheses here, minus 8 to the 0, if you do the exponent first, this is negative. If you don't get this, go back and watch what we went over with the order of exponents until it's completely clear why the first example was 1 and the second one here was negative 1. Now, is this 1 or 2? Again, exponents first. X to the 0 is 1 times 2. You do the coefficient after that. You don't go from left to right. You have to get this, or polynomials are not going to make sense. A lot of the trouble people have with polynomials is they just read the terms left to right. When you have a polynomial expression, you're evaluating it. You always evaluate the power first and then the coefficient out in front. So here, x to the 0 is 1, and then we multiply by the coefficient 2. So this is actually 2. And hopefully the next one here we'll put... Okay, so now you have parentheses. If there are parentheses around the base, now we can just say, okay, to the 0 power is 1. Okay, so that's the difference. Okay, I'm not going to do all of these. Okay, let's do this. 6 to the negative 2. Remember, negative exponents means 1 over. So this, this is 1 over 6 squared. So that's 1 over 36. Negative 3, all raised to the negative 2. I would just worry about getting rid of the negative power first. So I'm going to say it's 1 over negative 3 squared. And then I'll worry about negative 3 all squared. Since the parentheses are around the negative 3, it's negative 3 squared, negative 3 quantity squared, which is 9. So this is positive 1/9. Again, without the parentheses in here, this would be negative 1/9. Okay. Yeah, be careful here. Real common mistake here is to try and add these together to get 1/16. So if I put in 1 over 16, it's going to say it's wrong. So I have to write them as fractions. So you cannot, with exponents and powers, they work well with multiplication and division. They do not jive with addition and subtraction. This is something you have to have in your mind. When you have terms, addition and subtraction, you generally, there's no rules that you can combine stuff like this. So in this one, we can't say that 9 to the negative 1 plus 7 to the negative 1 is 16 to the negative 1 in the way that we could say 9 to the negative 1 times 7 to the negative 1 is 63 to the negative 1. We could do that. But this is adding. So this is 1/9 plus 1/7. And you have to add those fractions together. So I'm not going to add those fractions, but you have to get a common denominator and so on. Same thing here. Okay, we're getting into some of the other rules. Let's go back to, I want to go back to, we can really put together a number of rules now. So I want to go back to this one that we saw just a second ago. This is a really common application of a number of different rules. You got the product, you got the second product and quotient rules, right? Because you got a big fraction inside here, but then you're using power to a power because you're going to distribute the power across a bunch of stuff. So what is this going to be? It's going to be, I'm going to distribute the 4 across. So it's going to be x to the 8th, 2 times 4, y to the 4th, all divided by, actually, so I should start with a big fraction. X to the 8th, y to the 4th, all divided by 4 to the 4th. Again, it's one of those powers. It's 2 to the 8th, which ends up being 256. So 4 to the 4th is 256. 64 times 4. And then z to the 3 times 4, z to the 12th. So it's x, you distribute the 4, x to the 8th, y to the 4th, over 256, z to the 12th. Okay, let's do the last two. There's 2 more rules. They have to do with fractions. And so really, they're not new rules, but they're convenient ones. You don't need them. You could use the other rules, but they occur so frequently that it's good to know them. And then once we do those two, we'll pretty much have all the rules. And then we'll just come back and just finish up some of the more complicated expressions here in the homework. So these last two rules have to do with fractions. Okay, so the first one says, what if you have not just a negative exponent, but you have negative exponents in the fraction? So it's not just a to the minus n, it's a to the minus n over b to the minus m. So what this says is, in a fraction, you can always switch a negative exponent to positive if you flip it. In other words, if it's on top, you put it on the bottom, and if it's on bottom, you put it on top. Now, we already have the one direction up here, right? Because this is really a to the minus n is a to the minus n over 1. So really, the number 7 just says you can put a negative exponent in the denominator, but what number 8 says, if you have a negative exponent in the denominator, you can just bring it up on top. So this is b to the m over a to the n. And this is actually pretty straightforward to see why this is true. Because a to the negative n over b to the minus m is a to the negative n times 1 over b to the minus m. But 1 over a to the n, we just saw is a to the minus n is 1 over a to the n from number 7. So we're going to use number 7 twice. The 1 over b to the minus m, we can go the other direction. So we can go the other direction and say that this is now b to the minus m. Right, so I'm using the 7th rule twice, but in different directions. So that's going to be 1 over a to the n times, and then minus a minus is a plus. So the minus m, the opposite of minus m is m. So that's b to the m. And now you put these two together, b to the m over a to the n. But the overall rule to remember is any negative exponent you have in a fraction, just change it from top to bottom or bottom to top. The last rule, and this is the last one, says, what if you have a fraction raised to a negative power? And what this says is that this is going to be the reciprocal raised to the positive power. In other words, if you're raising a fraction to a negative power, just flip the fraction. And there's a number of different ways to see this as well. We could distribute the exponent and then use the previous rule. So a to the minus n over b to the minus n, and then, flip them so it's b to the n over a to the n, and then put it back together. But there's an even nicer way here. Notice that a over b to the negative n is equal to a over b to the negative 1, all raised to the positive n. So this is power to a power. So since negative n is negative 1 times positive n, I can take a over b, raise it to the negative 1 power, and then raise that power to the n. But a over b to the negative 1, remember that this stands for reciprocal. So a over b to the negative 1 is 1 over a over b. And remember that when you're dividing by a fraction, you invert and multiply. So the reciprocal of a over b is b over a. So this is b over a to the n. Now, maybe the other way of thinking about it is a little bit easier, but this is the way I like to think about it. The negative exponent means take the reciprocal, and the reciprocal of a over b is b over a. Okay, so here's a good example of one of those. The one where if you have a negative exponent in a fraction, you can flip it. So we can immediately flip this and say the 6 to the negative 5 on the bottom is going to come on top. And the 3 to the negative 4 on the bottom is going to be 3 to the 4th. Now, I could do 6 to the 5th, but I'm going to use a little shortcut here. Be smart. Remember, 6 is 2 times 3. So if I break up that as 3 times 2, all raised to the 5th, all over 3 to the 4th, then I can distribute the 5 and get a fraction that has 3 to the 5th times 2 to the 5th. All divided by 3 to the 4th. And now I can see, oh, 3 to the 5th over 3 to the 4th is 3. So I got 3 times 2 to the 5th. So instead of evaluating, don't evaluate the 6 to the 5th and the 3 to the 4th. Break it up into the prime factors, cancel stuff. So it's 3 times 2 to the 5th. So 32, which is 96. All right. Let's just do a couple more. Again, a lot of people will try and distribute the exponent first here. If it's just a fraction raised to a negative power, I would just flip the fraction first. I'd say this is just 2/5 all cubed. To me, that just seems like a simpler way to do it. And now, on one like this, remember I said that all of these rules work for any exponent. So we can now apply them to negative exponents. If I add the exponents here, negative 10 plus 7 makes an exponent of negative 3. Now, they don't usually like to have your answers end up as negative exponents. So I'm just going to write this then as 1 over x cubed. Okay, it says use positive exponents only. So this would just be 1 over x cubed. Let's do the last one. So we'll do the last one. If you can do this, you can do pretty much anything. Okay. Actually, let me copy this one down. I'm not going to try and do it here. Okay, so I'm going to copy this. We'll work through it, and this will be the last thing we do. So the thing to keep in mind here is don't try and work with fractions. A lot of people will immediately use the fraction rule, the last few rules, which says a negative exponent is 1 over. And they'll do the fractions inside the parentheses, and then they have to do 1 over the fractions. What you want to do is work with the negative numbers, the negative exponents, as long as you can, because that way you don't have to deal with fractions. So just do all the rules with the negative exponents, and then at the very end, if you have negative exponents, you can make them positive. So let's just distribute here. So I start off with distributing the negative 1 exponent across here. So I've got 5 to the negative 1 times negative 1. So I've got 5 to the first times z to the positive 2 x to the negative 1 times, distribute here, 4 to the negative 2 times z to the negative 4 x to the negative 10, all divided by 3 squared times z to the negative 4 x to the negative 6. All right. What I'm going to do is I'm going to collect all of these numerical coefficients together, because that's going to be kind of like the numerical part. So here we've got 5 on top. Then this 4 to the negative 2 is going to go on the bottom. So it's going to be 5 over 3 squared, which is 9, times 4 squared, which is 16. So that's all going to be the numerical coefficient. And now what I'm going to do is collect all of these variable powers. I've got a power of x, x to something, y to something, z to something. And I'm just going to add and subtract the exponents. So for x, I've got negative 1, negative 10 on top. That's going to make a negative 11. But then I have negative 6 on the bottom. So I have to subtract that, but remember it's a negative number. So it's negative 11, subtract negative 6, which is really plus 6, giving me negative 5. So I have x to the negative 5. Y. Oh, there's no power of y. I lied, sorry. It's just x and z. Okay, so there's no y. Now what about z? We've got 2 and negative 4. So 2 minus 4 would make a negative 2, but then we've got the negative 4 on the bottom. Subtract a negative 4. This is the most common mistake, is people forget that when you're subtracting a negative exponent, it's really adding that. So 2 plus 4, so 6. So we've got z to the 6th, x to the negative 5. Now all I have to do is just put the z to the 6th and the 5 together on top, and the x to the negative 5 is going to go on the bottom as x to the 5th. So I've got 5. And notice 5 doesn't cancel with 9 or 16. Those are all prime powers. So 5 z to the 6th, all divided by 5 z to the 6th, all divided by 9 times 16 is 144. So that's going to be 144 x to the 5th. So 5 z to the 6th over 144 x to the 5th. Yep, I did it again. Negative 2 plus 4, not 6. Sorry. Negative 2 plus 4, of course, is 2. So that's going to be, it's going to be, sorry about that. Even the best make the arithmetic mistakes. Just gotta super close attention. Negative 2 plus 4 is positive 2, not positive 6. I'm talking and explaining and thinking and trying to think about several different things all at once. I apologize for these little arithmetic mistakes. And it just goes to show that everybody makes arithmetic mistakes, and it's something that you need to be on the lookout for. Okay. All right. So again, if you could do this, you can pretty much do any of these problems. So these are exponent rules. This was a long video, but there's a lot to go through. The next section, we're going to be doing scientific notation, which is an important application of this, especially if you take other non-math classes. And then we're going to move on to polynomials, which is a super important topic that we're going to spend most of the semester on. All right.